So 1 comma 2 comma 3 start. My name is Dr. KCH Apparao, working as a associate professor in a mechanical engineering department. Okay, today I would like to explain about the definition terminology of conduction of heat transfer. How to find the conduction in the slabs, in cylinders, in sphericals. What is the formulas to find out the rate of heat transfer in slabs, in cylinders, in sphericals? We'll see. So before going to that one, we'll see overall heat transfer coefficient. You know that heat transfer coefficient, according to Newton's cooling law, Q is equal to HA into temperature difference, T solid minus T fluid. So H is the heat transfer coefficient. You know this one. We already discussed in the previous class also. But what about the overall heat transfer coefficient? What is the meaning of overall heat transfer coefficient? Suppose so this formula only for the one layer of any substance. If there are more number of layers, just like heat transfer, this is the slab. If you consider, this one is the heat is transferred from this atmospheric air to this solid to outer surface to room temperature, another atmospheric conditions. So here uh, here H HA or HA is different. Heat transfer coefficient here is different of the body. Here heat transfer coefficient is different. Okay, you can combine all this one for finding of this one, just like you have to consider all this one, and you have to find this one. You have to find the overall heat transfer coefficient. We'll see what is overall heat transfer coefficient, then you can understand properly. The overall heat transfer coefficient is defined in terms of total thermal resistance between the two fluids. Total thermal resistance between the two fluids. First of all, we'll see what is thermal resistance. Okay, you know that electrical analog formulas. First mode is the conduction. According to Stephen Boltzmann law, formula is equal to suppose this is the slab. This one is the temperature T1. This is the temperature T2. So heat is transferred from temperature T1 to T2. This is the thermal conductivity. Then Q is equal to area is equal to A. Q is equal to Ka into T1 minus T2. This is the formula. You know this one. Thermal conductivity. We can write like this one. T1 minus T2 by Ka. 1 by Ka. 1 by Ka. Okay. So this 1 by Ka is nothing but thermal resistance. Thermal resistance. Okay. Thermal resistance. So it means temperature difference by something. So that is called thermal resistance. So initial temperature minus final temperature by remaining terms. So Q is equal to T1 minus T2 1 by Ka. So this 1 by K is the thermal resistance. If you take one more slab is there, like this one. One more slab is there. Okay. It means so here this is the one slab, this is another one. So this one is the thermal conductivity K1, this is the K2. Area, suppose you can take area is equal to uniform or different also. Okay. So this is the temperature T1, this is the T2, this one is the T3. Okay. So then formula is equal to mm, so adding initial temperature, so T1 minus so T3 by 1 by K1A plus 1 by K2A. So here the combined thermal conductivities. So this is the thermal resistance. This is the thermal resistance of the first slab. This is the thermal resistance of the second slab. Okay. So here overall heat transfer coefficient is defined as the total thermal resistance between the two fluids or two slabs. Okay. Here uh, overall heat transfer coefficient to H, it is represented by U is equal to 1 by, it means total thermal resistance, that is the 1 by K1A plus 1 by K2A. So this is called, according to this one, that is called overall heat transfer coefficient. Okay, we'll see here according to the PPT what is thermal resistance, overall heat transfer coefficient. Okay, so here just I want to uh, explain about the electrical analog formulas also. I forgot that one. Suppose according to Stephen Boltzmann law, Q is equal to, so temperature T1 minus T2 by 1 by Ka. Okay, so it means this is the temperature T1 according to this slab. This is the temperature T1. This is the temperature T2. Heat transfer from temperature T1 to T2. This is the thermal conductivity. This one is the of this body or this plate K. Area is equal to A. Okay. So temperature starts here. Conduction takes place. This is the thermal resistance and reaches to temperature T2. So this is the rate of heat transfer Q. Okay. No? So this shows the thermal resistance. Thermal resistance is equal to here 1 by K. This is the thermal resistance. So we can rewrite like this one. So Q is equal to initial temperature T1 minus final temperature T2 by R. Okay. This R is the thermal resistance, RTH. RTH is equal to nothing but 1 by K for one slab. Okay. If you take more number of slabs, you have to add all the thermal resistance of the corresponding slabs or corresponding uh, that objects. Okay. So that is called, that shows the overall heat transfer coefficient. We'll see one more example also. So now we'll see heat conduction in slabs. This is the, just I am giving the formulas. What is the formula for the calculation of heat conduction in slab? Just you are taking the one slab. The initial temperature is the T1. Final temperature is equal to T2. This is the rate of heat transfer, which is normal to the homogeneous body. Okay. So then this is the thickness of slab is equal to L. Okay. Thickness is equal to L. Okay. So then the final formula is equal to, you know that according to Fourier's law, by using this boundary condition x is equal to 0 and at x is equal to 0, t is equal to t1, at x is equal to L, t is equal to t2. You apply the boundary conditions and you will get this formula. The final formula is like this one. That is the thermal conductivity area by T1 minus T2 by L, thickness. In the previous also forget this thickness, L by K1. Sorry. Here also L by Ka, because you have to construct the thickness. Okay. So by thickness, you can rewrite like this one. This is the temperature difference by L by Ka. L by K is the thermal resistance. Okay. So thermal resistance of this slab. If you consider more number of pieces, just like this is the one slab, this is another slab, this is another slab, this is the temperature T1, this is T2, This one is the T3. This one is the T4. Okay. Electrical analog formula is equal to T1 starts resistance of this first one, T2, T2 resistance, T3, T3 through resistance, and the T4. Okay. So this is the T1, T2, T3, T4. This is the thermal resistance 1, thermal resistance 2, thermal resistance 3. Okay. RTH1 is equal to L1 by K1A. RTH2 is equal to L2 by, because this is L1, this is L2, this is L3. Area A1, A2, and A3. Okay. So L2 by K2A and RTH3, third one, L3 by K3A. Okay. So it means oral heat transfer coefficient is equal to total R. Okay, 1 by R. R is equal to RTH1 plus RTH2 plus RTH3. Okay. It means the final equation. So that shows the heat conduction in the composite slab. This is the formula for the composite slab. For the composite slab, rate of heat transfer Q is equal to initial temperature minus final temperature T1 minus T4 by RTH1 plus RTH2 plus RTH3. Yeah? So it means T1 minus T4 by RTH1 means L1 by K1A 1 plus L2 by K2A2 plus L3 by K3A2. Okay. So this is the formula. So this is the formula for the heat conduction in composite slabs. Composite slab. Here also you can observe the heat transfer in composite slabs. So here you will see the formula composite slab written Q&A. Okay. So this is the formula. You can consider this one. Next to heat conduction through hollow cylinders. This is a hollow cylinder. Inner radius Ri. Outer radius of the cylinder is equal to R naught. Length of the cylinder is equal to L. So initial temperature, inner temperature is the T naught, and the outer temperature is equal to, this is the Ti, this is the T naught. Then what is the formula? So we can derive this one by the help of Cartesian heat conduction equation cylinders by in one-dimensional direction by using the boundary conditions. The final equation just I am giving here. This is the final condition. Rate of heat transfer in cylinders, in hollow cylinders. Okay. So this is the 2 pi KL into temperature Ti minus T naught by inner temperature, high temperature, outer temperature is the low temperature. Heat transfer takes place from inner to outer. Okay. Ti minus T naught by Ln R naught by Ra. This is the formula. Okay. 2 pi, you know that constants. K is the thermal conductivity. L is the length of this piece. By using this formula, you can find out the heat conduction in cylinders. Here also composite cylinders. If there are many layers are there, same formula, electrical analog formula. This is, for this one, electrical analog formula is equal to, this is the Ti, thermal resistance, and T naught. Thermal resistance is equal to Ln R naught by Ri by 2 pi Kl. This is the thermal resistance. If there is one more layer, you can add this one. Thermal resistance. This is T naught. This one is the T1. Okay. So this is the ln. Here R2 by R1 2 by KL. Okay. Here R3 by R2 2 by thermal conductivity K1. This is K2 L. L is common thing. Okay. So in this way, just like you can add this one. So here Q is equal to initial temperature T1 Ti minus T naught by thermal resistance ln R2 by R1 by 2 by K1L plus ln R3 by R2 by 2 by K2L. So this is the formulas. You can find out the composite cylinders, composite layers of cylinders. Okay. So in the same way, just like we'll see, what is the heat conduction through hollow spheres? This is the formula. You can remember this one. Q is equal to 4 pi K into R naught Ri into Ti inner minus outer temperature by R naught minus Ri. Okay. So this formula you have to remember this one. The finding the rate of heat conduction in spheres. Okay. Here also you can write like electrical analog formula means so Q is equal to only temperature difference Ti minus T naught by R naught minus Ri by 4 pi K R naught Ri. Okay. So more number of layers you can add this one. The first one is the initial one. So R2 R1 next to R3 R2 like this one. Okay. This way you can find out heat conduction through hollow spheres. Okay. So this is the formulas. Next we'll see critical radius of insulation. What is critical radius of insulation? Or critical thickness of insulation? We know that according to Stephen Fourier's law. So if you consider this slab, this is the L, thermal conductivity K, area A, temperature T1, temperature T2. Okay. So Q is equal to formula is equal to Ka into T1 minus T2 by L. Okay. So it means K is the thermal conductivity, that is the constant. Q is directly proportional to temperature difference, that is very important. Also Q is directly proportional to area. This one also very important. Okay. So next to this Q is indirectly proportional to thickness. Okay. If the thickness increases, heat conduction will be decreased. Heat conduction will be decreased. So here also critical radius of insulation means if the thickness or critical radius of thickness, if the thickness increases, rate of heat transfer should be decreased. In case of slabs, it is okay. If the thickness of the slab will increase, the rate of heat transfer Q will be decreased based upon this Fourier's law. So it is good, but in case of cylinders, so it is not. So because in case of cylinders, initially the rate of heat transfer will be decreased with increase in the thickness. Suppose this is the hollow cylinders. Hollow cylinders. So this is the hollow cylinder. This is the thickness L1. Okay. So if the thickness of cylinder increases, initially Q will be increased, Q will be decreased. Okay, Q will be decreased. But then if you increase this thickness of this cylinder, so Q will be increased instead of the decrease. But in case of slabs, it will be decreased, no problem. But in case of the cylinders, sometimes up to some point, the thickness, the radius of heat transfer, the conduction, heat conduction is increases with respect to increasing the thickness of the cylinder. Why? What is the reason behind this one? You'll see. So that point is called, up to certain thickness, the rate of heat transfer will be increased. After that, the rate of heat transfer will be decreased. That point, that is called critical thickness of insulation. So you'll see, adding of insulating material on the surface does not reduce the amount of heat transfer always. That is obvious. You know this one. So in fact, under certain circumstances, it actually increases the heat loss up to certain thickness of insulation. The radius of insulation for which the heat transfer is maximum. Okay, that point is called critical radius. The formula for this critical thickness RC is equal to K by H. We'll see what is the reason behind this one here. In planes, okay, if the thickness increases, the radius heat transfer rate will be decreases. Okay? But in cylinders, in cylindrical objects, in spherical objects, but it is not right. Up to certain thickness, certain point of thickness, the rate of heat transfer is increases. After that, the rate of heat transfer will be decreased. Okay, a decrease in the convection resistance, because we'll see the formulas of this one. Up to certain point, heat transfer rate will be increased. After that, decreases. This point is nothing but critical radius of insulation. Critical radiation. It means Q will be increased, and instead of decreasing here, it will be increased. It increases up to certain point, certain thickness, or certain radius of thickness, radius of cylinders. So that thickness, that radius is nothing but critical radius of insulation. You can find out that one, that the formula is equal to RC is equal to K by H. You know that K is the thermal conductivity, H is the heat transfer coefficient. So that is the final formula. So we'll see what is the reason behind this one. You know this one here in this. Suppose this is the we're considering this is the cylinder. The inner temperature is equal to Ri, outer temperature is equal to R2. Okay. Heat flux is equal to small q. Thermal conductivity of the material is equal to K. Q is the heat transfer rate. You know that heat transfer means so heat transfer of heat from the solid to liquid, or liquid to solid. Solid to solid, that is the conduction. Solid to liquid or liquid to solid, that is the convection. You know this one. Here, so two types of conduction will be observed here. One is the two types of modes will be observed here. One is the through this material, so from inner to outer, that is the conduction. Through conduction process, heat will be dissipated, heat will be conducted. Okay, from this material to atmosphere, so that is occurs by convection process. So conduction process and convection process, this is the conduction process resistance, this is the convection process resistance. There are two resistance of there here. We'll see. So if you want to find the steady state condition, dq by d r naught is equal to 0. If you derive this one, you will get the final formula, RC is equal to K by H. But here you can observe two types of the resistances. One is the conduction resistance, another one is the convection resistance. So in conduction resistance, this is the R naught by Rn. R naught is the outer temperature. outer radius of cylinder, R is the inner radius. If you increasing R naught only, you are increasing R naught by for the thickness. If you increase the thickness of the layer, it means R naught will be increased. Okay. If you increase here, here R naught will be increased. Here also R naught will be increased. But here it is under the logarithmic principle. Under the logarithmic principle. Here directly R naught. So the increase of R naught here is very more compared to ln R naught. Okay. It means if you increase the R naught radius of this layer, this resistance will be increased more compared to conduction resistance. Okay. It means this parameter, this R naught is increases. If this increases, it means comes into just like top side numerator positions. It means automatically due to this resistance, heat transfer rate should be decreased, but due to this resistance, heat transfer rate is increases. Okay. So because of that one, Q will be increased because the conduction resistance of the convection is more than the resistance of the conduction. Okay. Due to this reason, up to certain radius, the heat transfer rate will be increases, after the decreases. That is called critical radius of insulation. This principle is very important for the just adding of the insulation on electrical wires and insulation material and the steam pipes like this one. Some cases heat dissipation is required. Some cases heat insulation is or heat controlling of heat loss is important. So for those applications, the finding of critical radius of insulation is very important. Okay. So this is the what is the effect of change in outer radius of hollow cylinder. So this thermal resistance of conduction increases with increasing in outer radius of hollow cylinders. This one. So next, fins is the external surfaces. The advantage of the external surfaces, uh, for the to increase the rate of heat transfer. Rate of heat transfer, because Q is equal to Ka into dt T1 minus T2 by L. So area, if you increase the fins means area will be increased. So Q is directly proportional to area. If the area increases, so rate of heat transfer also increases. Okay. So the surface of the engine is very less. This is, if you add some pins on this one, automatically area of this area of this engine will be increases. If the area increases, automatically rate of heat transfer will be increased. It means heat is dissipated from the engine to atmosphere. Okay. So these are the different books to refer these topics. Thank you for the listening this class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.